Polish versus rot. During development, quality primarily improves via polish or multiple app refinement. After development ends, quality primarily worsens via rot or multiple context change. We strive to organize and clarify a variety of well-known details about polish and rot, that they affect all programs and standards, that all programs and standards have bounded lifespans, and that analysts, programmers, and testers can only affect quality in limited and specific ways. Polish and rot correspond to the two forms of emergence, change that occurs inside and outside of projects. All development and refactoring happens because of context change. Technical debt is the choice of when and how to respond. Traditionally, technical debt corresponds to deferring polish, but another form also corresponds to deferring rot. First, we list many examples of app refinements and context changes in order to provide an empirical foundation for this chapter. Then we contrast polish with rot to reveal aspects of their natures. Then we delve into the mechanisms for increasing polish and deferring rot to clarify the economic trade-offs of technical debt. Finally, we combine polish and rot to define a wave-shaped upper bound on software quality. Examples. Listing many real-world examples of app refinement and context change grounds this chapter in empirical data. Examples of app refinements. The mechanisms of app refinement include multiple analyses, developments, refactorings, inspections, and tests, both within and across projects. They also include training, prior experience, pairings, and checklists. Serial app refinement within projects. Royce waterfall example. In his classic paper on the waterfall, Winston Royce recommended developing software 3 times within each project. First, as a paper design, with 50 times more detail than for a comparable hardware system, then as a quarter-scale prototype, and finally as a full-scale system. Each stage informs the rest of the project. Debugging example. Debugging usually proceeds via serial app refinement. Developers try one potential solution after the next, hopefully the most cost-effective or highest odds of success first, until they fix the bug. Testing example. Testing usually proceeds via serial app refinement. First, developers write some unit tests and then run some manual tests on features in isolation as they write code. Then testers consistently retest each feature in the context of the whole program. And finally, users do alpha and beta testing of the whole program in the context of the real world. Parallel app refinements across projects. Software engineers develop many programs in parallel independent projects, and then the winners become standards. Program examples. In hot markets, many companies develop programs in parallel, and only the most competitive survive. In the 1960s and 70s, many companies wrote database and accounting programs for mainframes, and Oracle won. In the 1980s and 90s, many companies wrote word processors and spreadsheets for the PCs, and Microsoft Office won. In the 2000s and 10s, many companies wrote communication and game programs for mobile phones, and Snapchat and Pokemon Go are doing well, even though the race continues. Library examples. Developers often implement algorithms and protocols a variety of times, and then committees select the best ones and add them to each standard library, for example, the Java and .NET libraries. Standard examples. Standard organizations like the Internet Engineering Task Force, IETF, Institute of Electrical and Electronics Engineers, IEEE, and Object Management Group, OMG, bring people from a variety of project-sponsoring organizations, companies, government agencies, open source projects, together to work in parallel on each revision of each network and communication standard. Large working groups bring 10, 20, or more organizations together. The participants in each working group collectively revise their standards until they become effective. NIST example. When the U.S. National Institute of Standards and Technology, NIST, created the Advanced Encryption Standard, they considered 15 different algorithms and selected Rijndael. When NIST created the Secure Hash Algorithm 3, they considered 51 different algorithms and selected Kachik. Serial app refinements across projects. Stepping close to look at individual programs and standards shows that sponsoring organizations refine them through long series of projects over decades. At each step, analysts and developers attempt to keep whatever works and to improve whatever doesn't. Program examples. All enduring programs evolve through a long series of projects. Microsoft Windows evolved through many major versions, 1.0, 2.0, 3.0, 3.1, NT, and so on. Microsoft Office for Windows has evolved through many major versions, 1.0, 1.5, 1.6, 3.0, and so on. Standard examples. Fortran has evolved through many standards, 1, 2, 3, 4, 66, 77, and so on. Secure communication protocols have evolved through many standards. SSL1, SSL2, TLS 1.0, TLS 1.1, and TLS 1.2. Secure hashing algorithms have evolved through many standards. SHA-0, SHA-1, SHA-2, and SHA-3. Both parallel and serial app refinements across projects. Stepping back to look at programs and standards in their contexts shows that rich ecosystems encourage improvements. Programs and standards improve both in serial and in parallel at the same time, improving on themselves as appropriate, as well as adopting the best ideas vetted in rival products. Program examples. Operating systems inhabit a rich ecosystem that includes Windows, Mac OS, Linux, iOS, and Android. Consider that Microsoft changed Windows 10 to use the App Store distribution model pioneered by iOS and Android. Games and utilities also inhabit rich ecosystems. Standard example. Programming languages inhabit a rich ecosystem that includes Assembler, C, C#, Fortran, Go, Haskell, Java, Lisp, Perl, Prolog, and Python, all of which evolve in their own ways. Encryption standards inhabit a rich ecosystem that includes the Blowfish, DES, RC, and Rindal families. Examples of context changes. The mechanisms of context change include growing data, evolving expectations and usages, as well as evolving hardware and software platforms. Note that arbitrary limits exacerbate data growth problems and that platform changes encompass reusing and porting code. Mechanisms of context change. Data growth. Perhaps the most classic example of software rot is data growth. As organizations accrue data and as databases get larger, access tends to slow down. Search results tend to become overwhelming. Users tend to run into arbitrary limits, and programs tend to become less usable. Expectation change. Users change their expectations as they get training and experience and learn to appreciate other sophisticated software. According to Sluicer's principle, whenever users interact with software, their expectations change, even if the requirements are otherwise perfect. Expectation change occurs both throughout projects and after releases. Users incrementally reveal their expectations as they slowly figure out what they want by discovering the possibilities, changing their minds, and demanding better features and more finesse. Evolving user expectations mean that nobody can describe programs once and for all. We believe that expectation change actually causes most software rot. Usage change. Programs and source codes often get used differently than originally intended or tested. For example, many customer relationship managers, CRMs, delete records that are closed. But CRM agents may want to reactivate those records later without losing information. So they use tricks like adding XXX into a name or adding a deleted field to mark deletion rather than actually closing the records. Such conventions complicate queries. Whenever CRM agents think of new bits of information to gather, they store them as text in existing note fields, which complicates queries. Ideally, those bits of information would reside in separate typed fields. For example, when users invoke features in different orders than testers, they may reveal previously undetected bugs and limitations. Architectural rot and code smells also occur when code gets used differently than programmers originally intended. Hardware platform change. Hardware platforms have evolved from mainframes to mobile phones, and most have died. The programs written for Mark I, Zeus, ENIAC, UNIVAC, CDC 6600, System 360, Cray 1, VAX, Altair 8800, and Apple II all died long ago. Their contexts have vanished. Adventure for the PDP-10 died. WordPerfect and Lotus 123 for MS-DOS died. A few programs might have survived since the 1950s or 1980s unchanged, but we don't know what they are, except maybe missile controllers. We expect that within 50 years, Wintel PCs and ARM mobile phones will also have died, possibly replaced by something based on pure graphics processors. Software platform change. Operating systems have evolved from monitors to CP/M to Windows 10. Programming systems have evolved from switch and patch cord panels to assembler to Java 10. Databases, user interfaces, communication protocols, and libraries have also evolved dramatically. With HTML and JavaScript, web browsers now act as freestanding software platforms that evolve in their own ways. Arbitrary limits exacerbate data growth problems. Programming has always involved a lot of working around arbitrary limits. As computers get more powerful and as memories get larger, arbitrary limits become less of a problem, but they never go away. Arbitrary limits arise from the difficulty of predicting the future and the real costs of unused hardware and software today. Maximum array size. On Wintel PCs, the maximum array size grew from 64 kilobytes per array on the 8086 and Win16 runtime to 2 GB for all data on the 8386 and Win32 runtime, to 2 GB per array on the Pentium and Win64 runtime. Java arrays currently max out at about 2G elements. As data grows and programs run into those limits, developers write workarounds. As computers get larger and those limits evaporate, developers remove the workarounds. IPv4 and IPv6. IPv4 used 32-bit network addresses in 1981 when the ARPANET only connected mainframe and mini-computers at government research laboratories, 10 years before home PCs could connect. Using 32 bits was huge at the time, but Bertram Meyer recently complained about the short-sightedness of 32 bits. IPv6 used 128-bit network addresses in 1998 after PCs started connecting to the Internet and before the Internet of Things became a thing. Using 128 bits was huge at the time, but we expect that someday, maybe in a century or so, someone will criticize IPv6 for the same reason, the short-sightedness of 128 bits. Network addresses could have started with 256 or 1024 bits, but that would have cost more in the short term. Governor limits. Today, Salesforce programmers wrangle with bulkification and governor limits, like the maximum number of queries and callouts allowed per web page, and the maximum number of records returned per query. These limits ensure that users won't have to wait long for web pages to load, but can cause problems for many otherwise reasonable programs. Platform change encompasses reusing and porting code. Developers usually focus on making their software work in the target environment, and they rarely worry much about how software could fail if ported to or reused in different contexts, which would occur in some arbitrary and unknown future. The following examples resemble installing a program on a faster computer linked to a bigger network and just presuming that everything will continue working fine. Therac 25 example. The Therac software worked fine on one platform that had hardware interlocks, safety features, but killed people when the company ported it to a different platform that lacked the hardware interlocks. Looked at one way, the software relied on the hardware. Looked at another way, the hardware masked potential bugs in the software. The context change revealed the discrepancies between how the software did work and how it supposedly worked. Ariane 5 example. The Ariane 5 contained software written for the Ariane 4, which wasn't even really used. The software worked just fine in the Ariane 4, but failed during the first launch of the Ariane 5, causing the rocket to explode. The context had changed. Using Ada may have increased the delusion that the Ariane 4 software would work without change in the Ariane 5. Telnet and FTP examples. Telnet and FTP have remained essentially the same for 50 years, but their contexts have changed dramatically. Telnet and FTP originally ran on the ARPANET. In the 1960s and 70s, the ARPANET needed little security. Only trusted researchers could access the privileged terminals. Anyone who misbehaved could have their physical access revoked. The ARPANET primarily exchanged documentation about science and technology projects, so most everyone could see and access the shared information anyways. PCs didn't exist, so nobody could hack into the network. The new network technology meant that obfuscation still worked. In that original context and for those original purposes, protocols like Telnet, FTP, and later RSH worked well. Today, Telnet and FTP run on the public internet. Anyone can get a PC and watch packets go past on the local network, or send packets to and receive packets from almost any IP address. People now use the internet to access information that truly should remain private, such as financial, medical, and voting records. Malicious behavior provokes few penalties unless someone gets carried away. Telnet and FTP still work on the internet, but everyone should avoid using them because they still transmit account names, passwords, and data in the clear. Encryption examples. DES, SSL2, and SHA-1 embodied the best cryptography of their times. Eventually, powerful computers made the small keys of DES easy to crack. SSL2 and SHA-1 have also been deprecated as better cryptography theory and more powerful computers loom ominously. Note that these encryption standards remain the same as they ever were, only the contexts have changed. Polish versus rot. Polish and rot mirror each other in many ways, as shown in Table 1. Contrasting them helps to reveal their natures. Definitions. Multiple positive app refinements. Multiple positive app refinements tend to improve quality. First drafts of programs and standards usually start out wonky and need many revisions to get good, just like all other forms of writing, including technical essays and poetry. In general, higher quality programs and standards emerge from lots of polish. Multiple negative context changes. Multiple negative context changes tend to worsen quality, but programs and standards don't spontaneously change for the worse on their own because bugs don't spontaneously multiply and algorithms don't spontaneously switch to worse versions. On rare occasions, bits in memory or on disk do spontaneously degrade, but restarts or reinstalls can fix those problems. The real sources of rot come from outside the program or standard and include changes in user expectations and usages, as well as changes in hardware and software platforms. All context changes reveal that the foundations below programs and standards really are shifting sand. Emergence spectrum. App refinement. Polish includes the whole spectrum of single, dual, and multiple positive app refinements. Polish usually emerges slowly through many positive app refinements, though the spectrum also includes single app refinements or doing things once. Individual app refinements rarely make much of a difference on their own because they provide the fewest opportunities for improvement. Note that most programs have many features that need separate polish. Context change. Rot includes the whole spectrum of single, dual, and multiple negative context changes. Rot usually emerges slowly through many negative context changes, though the spectrum also includes single context changes. Individual context changes rarely make much of a difference on their own, though some, like Y2K and Y2K38 date rollovers and the DYN and WannaCry malware attacks, provoke catastrophes. Cut both ways. Not all app refinements benefit programs and standards. Not all context changes damage programs and standards. Most of each actually improve quality, benefiting users, programs, and standards alike, even though some do worsen quality. So both app refinements and context changes cut both ways. App refinement. App refinements usually improve quality. As analysts, developers, and testers work on programs and standards, refining them through multiple analyses, designs, codings, inspections, and tests, whether in series or in parallel, quality tends to improve. App refinements sometimes worsen quality, which is called code entropy. Adding bugs during app refinement occurs routinely, but in our experience occurs much less often than quality improves. When programmers fail to clean up after changes or fail to refactor, the structure of code can degrade, making future changes harder. Context change. Context changes usually improve quality, helping users, programmers, and standards alike. Context changes include computers getting faster and memories getting larger, as well as operating systems and libraries adding features, improving security, and fixing bugs. In general, everyone should want context to improve because they should want to gain the benefits of the upgraded platforms. Context changes sometimes worsen quality. The term software rot applies whenever context changes cause problems for users, programs, or standards, such as data growth, expectation change, and platform obsolescence. Examples. In general, more powerful computers make programs run better, but not always. For example, powerful computers both strengthen and weaken cryptography. As embedded devices get faster processors and better sensors, users expect embedded programs to do more useful work, and they tend to become disappointed when programs remain unchanged. Timeframes. The time of discovery and fix can affect whether requirement problems and coding bugs seem more like polish or more like rot. Usually, quality peaks just as development finishes, at release. Before release. Quality primarily improves during development. In general, before the release of a program or standard, analysts fix requirement problems and developers fix coding bugs as they are found. In general, everyone interprets those fixes as polish. After release. Quality primarily worsens after development ends. In general, after the release of a program or standard, rot will reveal any remaining requirement problems and coding bugs. In general, these problems will remain unfixed and will accumulate until the next upgrade. Rot actually occurs all the time. Context change actually occurs both before and after release, or in other words, rot also occurs throughout development. For example, users often change their minds about goals during projects. We know of projects that competitors rendered obsolete before release, and architectural rot can occur as long as developers change code. Yet as long as a project continues, analysts, developers, and testers can potentially counteract rot. Natures of state. Finite and known. Users, analysts, and developers can only describe and implement finite known properties. Requirement and specification documents explicitly describe the desired finite and known features of each program and standard. Infinite and unknown. Everyone struggles to describe the enormous, complicated, and continually evolving contexts because they lack the time and energy to understand everything about their hardware and software platforms. Even though in theory platforms are finite and known, in practice they are so large that they are effectively infinite and much remains unknown to each analyst and developer. Nobody has the time to describe or implement infinite properties. Nobody knows how to describe or implement unknown properties. Platform examples. The enormous platforms provided by Windows and Linux and the enormous libraries available for Java and .NET are overwhelming. Requirement documents almost never describe the platforms below programs except in the most general terms. For example, quote, "The program shall run on Androids and iPhones." Great oral tradition example. Analysts and developers have enormous bodies of conventions, expectations, knowledge, and experiences that remain undocumented. Creating effective architectures and pleasing UIs still requires a lot of murky intuition and aesthetic judgment. Decades ago, IBMers referred to this body of knowledge as the Great Oral Tradition, and it continues getting larger for everyone today. Natures of change. Enumerated, explicit, and visible. Users and analysts tend to explicitly enumerate the desired changes of each project in requirement documents. In general, everyone can explicitly see and count the changes that users have requested. Changes to programs, specifically features, must be visible and explicit because users cannot use and testers cannot test what they cannot see. Infinite, implicit, and invisible. Infinitely many potential context changes could occur, so nobody can describe everything that must remain unchanged for a program or standard to remain vital. Most potential changes have low probability and should go unmentioned even though they could conceivably occur. Nobody can analyze the risks of an infinite number of context changes either. Many context changes easily elude detection. For example, users can easily see when a UI becomes unfashionable, but they cannot see when a security system becomes unsafe. Security example. The context stabilities needed for AES and SHA-3 to remain vital include that computers won't get more powerful faster than current growth curves estimate, that quantum computing won't become practical anytime soon, that nobody will find low-degree polynomial algorithms for NP-complete problems, that no new theory will break AES or SHA-3 directly, that AES and SHA-3 won't fall out of fashion in favor of different technologies, that new hacking techniques won't expose hardware and software platforms in ways that render AES and SHA-3 moot, that clairvoyance won't become common, and that extraterrestrial aliens won't invade. Note that improved theories in computers have already undermined many security standards. Agents of change. Project team members. Project team members exert a good deal of control over programs and standards because they can take deliberate actions to make programs and standards behave in specific ways. Users and analysts can indirectly modify programs and standards by changing the requirements. Developers can directly modify programs and standards by changing the source code. People in computer science, requirements engineering, and software engineering study how to take control of and thereby improve programs and standards through explicit actions during projects. Other people in society. Almost nobody has control over the context of programs and standards because other people in society cause most context changes. The causes of rot remain far beyond the control of anyone on project teams. Some context changes occur predictably in general if not in specific. Intel, ARM, NVIDIA, and AMD continually tinker with their CPUs and graphics processors, occasionally adding instructions and cores. Microsoft, Apple, Android, and Linux make major upgrades to their operating systems every few years. Standard organizations upgrade programming languages and protocols every 5 to 15 years. Other changes defy prediction. Nobody predicted that the U.S. National Security Agency would give tools to hackers to create WannaCry. Nobody predicted that cryptographers would find weaknesses in Diffie-Hellman and SHA-1. Users continually change their expectations and usages, and in general, nobody can predict what users will want next. The fact that different agents of change control polish and rot helps to explain why solving the polish problem cannot solve the rot problem. Users, analysts, and developers can only add more polish, which only affects half of how quality changes. Until someone learns to predict the future changes in expectations, usages, and platforms, they will never solve rot. Specification languages and model-driven development will not solve rot either. Testability. Positive past program changes can be tested. In general, test plans work well for the specific positive properties of programs. For example, one can test that records get inserted, updated, and fetched in a database. Note that testing focuses on properties that already exist in working programs from the known and finite past. Negative future context changes cannot be tested. In general, test plans do not work for the negative properties of contexts. No plan can test that a context has not changed in an unexpected way. No plan can test that future context changes won't reveal any bugs. No plan can test whether security algorithms like AES and SHA-3 remain secure. No plan can test that FTP remains fit for some purpose. No plan can truly test ilities like the portability or reusability of a program without knowing the specific contexts that will arise. No plan can test whether users did or didn't change their minds about what they want, though of course they eventually will. Note that context test plans would ideally detect the changes that will occur in any of the infinite possible futures shortly before they materialize. Detecting that a platform will change many years ahead does not help because obviously many things will change by then. Edgar Dijkstra knew about the limits of testing 50 years ago when he wrote, "Testing shows the presence of, but not the absence of bugs." We would add another caveat about contexts. Testing shows the presence of bugs in programs, but neither the absence of bugs in programs nor anything about context changes. Thoroughly retesting each program in context before delivery is a best practice, but nobody can afford to retest programs every day as contexts incrementally evolve. Equations. We offer the sunrise and decay equations as the key patterns for how quality changes over time, as shown in Table 2 and Figure 1. Note that each equation expresses a different rate of diminishing returns and that the sunrise and decay equations mirror each other. Sunrise. The sunrise equations describe the shapes of polish, showing how quality improves over time. Small statistical samples can capture the underlying truth with luck, or get it totally wrong without luck, or anything in between. The sunrise equations show how to understand the quality of small statistical samples, or equivalently the incremental benefits of each additional sample, or equivalently how many samples are needed to achieve any desired degree of certainty. Feature example. When one user asks for feature X, he or she could agree with all of the users, but analysts have no guarantees that the next user won't contradict the first by having a different and better idea. When 3 users ask for feature X, analysts have more certainty, but still not a lot. For example, analysts may have asked 3 users in the support department, but may not have asked anyone in quality control, accounting, or management, users who wield far more clout in the organization. Analysts may not even think to ask those other users. Analysts must necessarily start discovery with small samples, but small samples invariably lead to at least some mistakes, like wrong or missing requirements. Asking everyone takes a long time and costs a lot for large user bases. Decay. The decay equations describe the shapes of rot, showing how quality worsens over time. These equations model atomic decay in physics and fund payouts in economics. Fractal example. One could also think of decay in terms of the function f of n equals 1 minus epsilon to the n. Robert May's logistic map, Benoit Mandelbrot's set, and Edward Lorenz's attractor all have some initial values that have predictable outcomes and other initial values that have unpredictable outcomes. But telling them apart can be tricky. In the unpredictable cases, the discrepancy between initial estimates and final outcomes will become clear at some scale of n. For large error rates, such as epsilon equals 2 to the minus 6, discrepancies will show up quickly. For tiny error rates, such as epsilon equals 2 to the minus a gazillion, discrepancies will show up only after a long time. For zero error rates, epsilon equals 0, discrepancies will never appear. The certainty C indicates the desired probability of success or level of quality, for example 0.99 or 0.9 or 0.5. Technical debt. Deferring polish. The classic concept of technical debt is stopping investment in polish early or cutting off development effort before release. This concept is often thought of as inadequate development, maintenance, or refactoring, and is well understood based on the Managing Technical Debt workshops. Deferring rot. Another concept of technical debt is deferring or ignoring rot. Keeping older programs alive means that they become less useful and risks accrue over time, whether anyone is aware or not. This concept has received scant attention. Root causes. The root causes of both forms of technical debt are context changes, which nobody on project teams can control. They appear in the guise of the costs of polish and the changes that evoke surprise. Surprises arise from the inability to predict the future. Making choices. Accruing technical debt means choosing to delay investing resources or to avoid responding to or coping with context changes. Both forms of technical debt defer development or maintenance by trading lower short-term cost for greater long-term risk. Balancing forms of debt. In one important sense, technical debt is the opposite of resource debt. Anyone who could borrow resources, time and money, to invest in development or maintenance could reduce their technical debt. Balancing resource debt against technical debt is a reasonable strategy for choosing how much technical debt to accrue. The trade-offs of increasing polish. Increasing polish improves quality by fighting mistakes up front during development. The mechanisms for increasing polish create and extend opportunities to find better solutions to the problems at hand. However, they cannot necessarily catch all mistakes. These mechanisms embody complex economic trade-offs because their benefits and detriments mirror each other as shown in Table 3. Practice. Proficiency and fewer mistakes. Dual and multiple development increase practice and reduce mistakes, as in practice makes perfect. Strong analysts, developers, and testers have practiced skills and decisions many times. High-quality programs and standards follow from a lot of practice in the form of multiple analyses, developments, inspections, and tests, whether in the current or previous projects. Redundancy and waste. Each additional implementation beyond the first takes additional work, which can seem redundant or even wasteful, especially as returns appear to diminish. Time. Polish. More implementations usually take longer to finish. The implementation that takes the longest tends to extend the deadline for everyone else, giving them more opportunities to think things through and to polish their results. Delay. Multiple development takes more time than single development, occasionally a lot more time, which slows down projects and results. Diversity. Better solutions. Diversity helps to find better solutions. Different analysts and developers using different approaches in different contexts often produce different results, doing different things well and different things poorly. Hopefully, each poor idea in one implementation will overlap an excellent idea in another. The greater the diversity, the greater the likelihood that one project or another will implement each feature well. Feature creep. The final versions of programs and standards based on multiple app refinements tend to contain more of the cool features from the union of all implementations. Because diversity tends to generate more cool ideas, programs and standards tend to ratchet or accrete features and flexibilities. Competition, creativity, and productivity. Healthy competition can increase both creativity and productivity. Many people struggle to find the problems within their own work, and input from outsiders can provoke constructive conflict, which can help to avoid settling for flawed results or groupthink. In organizations working on standards, like the IETF, IEEE, and OMG, competing companies, government agencies, and open source organizations collaborate with each other. Motivated partly by competitive spirit, participants strive to find problems in each other's work, as well as strive to avoid screwing up and looking bad compared to rivals. Exposes private information. Collaboration requires the sharing of information, so organizations cannot keep everything secret. Surprise. Learning. Ideally, multiple development evokes the surprises that drive learning as opposed to the proverbial insanity of rote repetition. Hopefully, through comparison, participants will discern the differences and then figure out which ideas and implementations work better than others. Remediation. Whenever someone else's code surprises a developer, he or she must often remediate his or her own code, which takes additional time and effort. Ignorance is bliss because it takes less time and effort in the short run. Economic trade-offs. Lower risks after release. Increasing polish lowers long-term risks. Increasing polish will most likely give programs and standards higher quality as perceived by users and possibly even longer lifespans. Greater costs before release. Increasing polish or doing more work up front raises short-term costs. The trade-offs of deferring rot. Deferring rot improves quality by fighting context change after the release of a program or standard. The mechanisms for deferring rot can extend the lifespans of programs and standards, however, they cannot necessarily avert any given expectation change or malware attack. These mechanisms embody complex economic trade-offs because their benefits and detriments mirror each other as shown in Table 4. Stabilize platforms. Keep legacy systems unchanged. Stable platforms enable legacy systems to endure longer without change. Techniques for keeping hardware and software platforms stable include stubbornly never changing them, maintaining backward compatibility, and emulation or virtual machines. Changing and sunsetting old platforms force bifurcation because everyone who has legacy systems on those platforms must either port them to another, possibly upgraded platform, or watch them die. Note that stabilization requires maturity because immature platforms change routinely. Forego platform changes. When platforms remain stable, users and developers must forego the benefits of changes, such as the increased power and energy efficiency of newer processors, as well as the bug fixes, security fixes, and new functionalities of newer operating systems and libraries. Whenever developers cannot use upgraded platforms, they may need to duplicate the upgraded features and bug fixes themselves. Clutter. Stable platforms often succumb to clutter. Marie Kondo argues that slogging through clutter in the real world wastes time and energy. Decluttering by removing old programs saves time and energy in the virtual world too. Users can voluntarily get rid of old programs, and vendors can voluntarily get rid of old platforms. Like a dust mop, sunsetting an old platform sweeps away many old, unsafe, incompatible, undesirable, unfashionable programs at once. Charging annual fees to keep apps alive in stores also encourages decluttering. Embedded system and cloud server examples. Embedded systems seem most amenable to stable platforms. For example, embedded devices in electricity meters can remain in place for 20 years or more. Even so, many embedded devices now have the ability to remotely upgrade the software. Cloud servers that communicate solely via web APIs can also remain stable for decades. Restrict platforms. Hide problems. Platform restrictions enable developers to hide some kinds of security problems. For example, one could physically separate the network so that programs that have weak security can endure longer without change. Forego context expansions. Platform restrictions make context expansions riskier. Context restrictions also prohibit legitimately accessing the device or program from centralized service centers on the Internet. Protocol examples. Restricting devices to communicate through serial ports or private networks enables Telnet, FTP, SSL2, and SHA-1 to continue running safely. But those contexts should expand only with great caution. Changing from physically isolated networks to virtual private networks may seem innocuous, but it increases risk. Adding any new device into a restricted network also increases risk. Stabilize subsystems. Factor out volatility. UIs tend to have much greater volatility than backends. Factoring UIs out to isolate or absorb change can enable backends to remain stable longer. UI developers can even run interference to work around some issues that would otherwise force backends to change. Distortion. Factoring increases distortion. Using Corba or web APIs complicates and distorts communication more than using native function calls. When designers guess wrong about what will remain stable or get unlucky, they may have to change the backend anyways, or even worse, have to change both the UI and the backend. When backends remain stable, changes to UIs become increasingly awkward as backends become increasingly out of date. Factoring a program into pieces can also cost a lot in its own right. Economic trade-offs 1. Lower short-term costs and risks. Deferring rot lowers short-term maintenance costs in terms of money to pay for upgrades and new programs. Upgrading legacy systems can require substantial resources which often belong to someone else. Recreating lost source codes tends to require tremendous resources. Deferring rot also lowers short-term risks. In general, legacy systems that worked fine yesterday will also work fine today. All changes that update or replace legacy systems today increase the short-term odds of breaking something. Organizations don't want to upgrade platforms because recertifying all of the apps that they support tends to be painful. When upgrading operating systems, some computers may be out for service and miss the upgrade, causing additional problems. Many people resent upgrades because without retraining, their skills can become out of date or obsolete. Greater long-term costs and risks. Deferring rot increases long-term costs. No longer having to support legacy systems frees up resources to work on more contemporary, more relevant systems, which should foster better software sooner. Deferring rot also increases long-term risks. The risks that someone will misuse each legacy system only increase over time, for example, due to outdated security. As long as Telnet and FTP exist, even if only to communicate with legacy systems connected directly to a server via a private network, someone will eventually say, aware of the risks or not, quote, "We can use FTP to transfer these top secret files." The longer a system remains stable, the more likely someone with vital knowledge about it will leave. Economic trade-offs 2. Greater short-term productivity. Deferring rot avoids the disruptions that lower short-term productivity. Users don't have to learn new or upgraded software. Admins don't have to install new or upgraded software. Developers don't have to develop or maintain software. Nobody will disrupt their learning curves. Organizations can apply all of those resources, that time and energy, to other problems. Lower long-term productivity. Deferring rot delays the benefits of better software for longer. Users can be trained to use older, less fashionable, lower quality software, but they will remain more disappointed and less productive for longer. Economic trade-offs 3. Economy of scale. One well-established principle of economics states that expanding the scale of the economy lowers costs. Platform standards extend the base of transferable skills and programs across more projects, people, and organizations. Stuck in the past. Keeping legacy systems alive denies the benefits of moving on to use better and more contemporary programs and standards. It enables stakeholders to remain stuck in the past. Delusion. Platform standards allow and even encourage people to believe that they can prevent all rot. In our experience, those who obsess over platform standards tend to deny all other changes as well. After all, people standardize platforms specifically to avert change. But platform standards cannot affect any other aspects of contexts, such as user expectations, user interfaces, and cryptography, which will all continue evolving beyond the influence of any platform standard. Everyone struggles with these economic trade-offs. DoD standard examples. The DoD routinely tries to control the contexts of their programs. DoD platform standards include the 1750A processor, the COBOL and Ada programming languages, and the Popcorn Linux operating system. These standards change rarely, and to improve, software projects must increasingly switch to other platforms that change more often. Commercial standard examples. Microsoft, .NET, Oracle, Java, and Apple, Swift, provide standard development platforms to the world that change routinely. All major operating systems provide their own standards for functionality and look and feel. The wave-shaped upper bound on quality. Combining the sunrise and decay equations together defines a wave-shaped upper bound on the quality of software as shown in Figure 1. The wave could appear as a triangle if plotted on a log-log graph as shown in the inset. The horizontal axis represents time with an unstated scale, and the vertical axis represents the level of quality or probability of success ranging from 0 to 1. The light curve shows quality as seen by analysts, developers, and testers, and the bold curve shows quality as seen by users who only receive the improvements after the release. Always imperfect. According to the sunrise and decay equations, human-produced programs and standards can never become perfect. Polish and imperfection. No finite amount of analysis, programming, and testing can guarantee finding all bugs before the release of a program or standard. No matter when anyone cuts off effort to perfect a chunk of code and moves on, he or she must rationalize that all remaining problems in that chunk of code will remain unimportant or unlikely, but nobody can ever know for sure. Only by committing unbounded or infinite resources to polishing code can anyone guarantee perfection. Obsessing over perfection, or undetected errors, will prevent analysts, programmers, and testers from ever moving on to new work. In other words, obsessing over perfection will prevent all further progress on everything else. Rot and imperfection. Continuing to use a program or standard means presuming that the context has remained stable and that all negative context changes so far have remained unimportant or unlikely, but nobody can ever know for sure. Even for embedded systems, manufacturers will eventually upgrade the hardware, developers will eventually upgrade the software, cryptographers will eventually deprecate the protocols, and users will eventually want different features. Only by stopping the rest of the world from changing can anyone truly stabilize the context and avert all rot. Bounded lifespans, evolve or die. Doomed. Rot kills all programs and standards over the long run. Programs rarely endure unchanged for more than a few years, and we don't know of any that have endured for decades, except maybe military software. For every program and standard that we have considered, we can easily imagine a platform or user expectation change that will render it moot. Of course, nothing else in the real world endures forever either. Ephemeral. All programs and standards live in the present and must eventually either evolve or die. The dashed vertical line in Figure 1 represents the end of the useful life of each program and standard. At best, sponsoring organizations develop programs and standards for the near future. Nobody can make their products endure for arbitrary lifespans, and in particular, nobody can make them endure forever. Commercial examples. In June 2017, Apple dropped support for 32-bit apps from iOS 11, and the older, less popular apps that didn't get maintained simply vanished. In 2018, Microsoft continues trying to drop support for Windows 7. Write once, run forever is impossible. Some people claim to have devised ways to write programs once that will run forever. Such claims are delusional because all polish, all software projects, come to an end, but rot never ceases. Writing a program once means that nothing will ever improve after release via polish, yet the program will continually undergo context change. Formal Methodists. In the 1970s, Edsger Dijkstra and Tony Hoare interpreted programs as algorithms, inspiring generations of researchers to support formal methods, and their legacy continues today. Algorithms and abstract data types formalize mathematical concepts. Specifications and models describe murkier user concepts. While specifications and models may remain correct forever, they will not remain useful forever. Even math and algorithms rot because as more math gets created, older math gets lost in the noise. Managers. Managers want simplicity and continuity. Some managers have argued that they could develop computer systems that would remain stable for years, but data will continue to accrete and expectations will continue to change forever. Java. Java claims to be write once and run everywhere. The statements and classes within Java may remain stable, but the contexts around Java will continue to evolve forever. Java user interfaces have already changed from AWT to Swing to JavaFX to Android, and they will continue to evolve. Secure network protocols will continue to evolve, so no version of Java libraries can endure forever. The end is rarely obvious until after it passes. In general, predicting the end of a life, the vertical dashed line in Figure 1, ahead of time remains impossible. In physics, everyone can know the distribution of the decay of atoms, but nobody can predict when any specific atom will decay, until it does. In software, everyone can know the distribution of the decay of programs and standards, but nobody can predict when any specific program or standard will decay, until it does. The rare situations where someone can predict the end of life include date-based rollovers like Y2K and Y2K38, and platform sunsets like Windows XP and 32-bit apps on iOS 11. Smooth and long-tailed. The decay equations have no obvious indicators where risk flips from good to bad. Ideally, everyone would stop using programs and standards before the probability of error crosses some threshold, say 90%, 50%, or 10%, depending on their risk tolerance. Statisticians can calibrate the decay equations to reveal those threshold crossings, but those equations cannot reveal what everyone really wants to know, specifically when each program or standard will decay or when the next crisis will occur. The proverbial frog should hop out of the pot before it boils. Someone should shut the barn door before the proverbial horses escape. Someone should maintain and upgrade each program and standard before the next crisis occurs. The slow and steady decline of rot enables laggards to continue using old programs and standards far beyond when they should, rationalizing the whole time that everything remains fine so far. Maintenance is the ongoing wrangle between polish and rot. As programs and standards succumb to rot, as their contexts change, project teams need to respond appropriately by adding polish so that programs and standards can adapt, remain relevant, and endure. Programs need continual redevelopment as data grows and as user expectations and usages evolve. Source codes need continual refactoring, recompiling, and relinking as hardware and software platforms evolve. A series of maintenance projects can extend the lifespan of programs and standards, as shown in Figure 2. The light curves show quality as seen by analysts, developers, and testers. The bold curves shows quality as seen by users, who only receive the improvements after releases. After maintenance stops, programs and standards will slowly fall out of use and fade away. All projects are finite prefixes of an infinite series of projects. Microsoft Office and Facebook will only get bigger for a long time to come. When they stop evolving, other apps will replace them. Fads. Finite lifespans can make programs and standards seem faddish, and some have argued that software fads are bad. However, fads show the flow of time. Slowly evolving GUI styles and features are markers for the age and functionality of programs. These markers provide valuable information to users for setting reasonable expectations about how programs should work. As expectations evolve, old software inevitably becomes less useful, and updating programs to make them appear contemporary shows ongoing maintenance. Notes. Inspirations. This chapter was partly inspired by Peter Newman's Risks column and by a paper by Dalal and Shalar in Software Engineering Notes, as well as by the List of Software Bugs page on Wikipedia. Those sources enumerate many problems and failures in software. This paper was also partly inspired by Malcolm Gladwell's discussions of inverted U-curves and, quote, no unmitigated good. Follow-up. This paper follows up on the essay, The Uncertainty Principle in Software Engineering, by Ziv, Richardson, and Klosch, and the chapter Unknownness, by providing a shape to the uncertainties and unknowns described. Applies to both programs and standards. The observations in this chapter apply to the qualities of both programs and technical standards or informal specifications, but not to the qualities of algorithms, which can be proven correct. We mostly avoid discussing formal specifications and models, though they are doomed as well. Processes. Processes in organizations for programming and support also undergo polish and rot. The word rot. The term software rot historically referred to software entropy. In the literature, software entropy seems to equal sloppy maintenance or inadequate refactoring. But those concepts have nothing to do with context change, which is the root cause of the problem. Perhaps we should use a different word than rot in this chapter to avoid confusion, but we don't know of a better word. The word hyperbolic. The hyperbolic decay equation has a problematic name because both Mandelbrottian equations have hyperbolic shapes. No matter where anyone stops development, he or she accrues technical debt.